One of the things we find out is that as things get small, they get weird. At least weird compared to what we're expecting to see at the macro scale. And those were some really surprising results when they first observed them, and it really made everyone aware that something is really confusing about what's going on with light. Let's see an example of that. Suppose we take a beam of light and we have our wavelengths. You can see we have a really wide range of light. And here we have our waves. You see that I have it superimposed. I'm just showing the bottom of the trough as my lines here. It doesn't matter if it was the bottom or the top. Totally doesn't matter. The key thing is we're just seeing either the maximum or minimum here for where the lines are. Now, when it hits into a little slit, what we expected to see with light is that if we put, some sort of a mask here, we should see the light go through as a straight little beam like this, right? Well, more straight than I just drew it, but you get the idea. That's what we're expecting to see. If it acted more like sound does, we'd expect it to spread out like this. Now here's something really surprising though. If I have two slits right next to each other, two small holes, I expected to see a beam of light come through like this, and a beam of light come through right here. And so I expect to see one bright spot here on the wall and one bright spot there on the wall. That's all I expect to see. If it were sound, I'd expect there to be loud spots and quiet spots as these waves are amplifying each other through constructive interference or diminishing each other through destructive interference. You can see that any of the spots where our lines are overlapping, like right here, I'm expecting to see amplification. Spots where it's totally in the middle, where one is high and the other one's low, I'd expect it to be totally canceled out. So this would be a quiet spot if we're talking about sound coming through two holes. But light shouldn't do that, because we know that light's a particle and it flies in a straight line until it finally hits a target where we detect the light. But this is really curious. If we were to stack a bunch of these slits together and we were to set a piece of photonegative over here, the negatives we used to use in cameras before the digital camera revolution, what we would see is we'd see stripes appear. And it's not the way that we expect them to either. Yeah, it would make sense to us to see two bright spots hitting over here if it was just going through like a particle. But it turns out that light actually is spreading out like a wave. So even though these beams are coming through, let me try to be fairly straight in my drawing of this, even though the beam of light is coming straight through right here, and I'm expecting to see only a spot of light right there. Keep in mind that if this is a photonegative, it's probably going to be a dark spot right there. There we go. That's a fairly straight line. I expect one spot here, darkness everywhere else. That's not what they found at all. They get this repeating stripe pattern, just like if it was behaving as a wave. Now we do know that light acts like a wave because we've described the wavelength of it. But we also know that the wave, the photon, is a particle. So is it a wave or a particle? It turns out it's really both at the same time, which is very surprising to people. We shouldn't be getting these stripes when it acts just like a particle. That should only be a consequence of it acting like a wave. So it's almost like it's choosing to act like a particle or choosing to act like a wave in its own logic, and we don't know what that logic would be yet. Here's something that's even more shocking. If we were to really dim down that light until the point where we only have one photon of light going at a time, and we have lots of photons going, but only one at a time, we would not expect to see any of this interference, right? What we should see then is, if I've got a slit here, here's our two gaps, two slits there, and I let one photon go through. Well, there's nothing for it to interfere with, right? I'm expecting that it's going to hit the wall, it's going to make a little spot on the photonegative paper. Then later on, a second photon's going to go through. And when that photon gets down here, it's also going to make a single spot on the wall. They're separated out in time. They shouldn't be interfering with each other. But they do. In other words, it's not that photon A and photon B are interfering with each other. Photon A is actually interfering with itself. Now that's weird. But they've repeated this experiment a number of times. And even when something is weird, if we have repetition and we have verification, we can't throw that data out. That's an important finding. And the fact that we can't understand it yet means that we have to add some sort of a nuance to our explanation. Obviously, something is very complicated in happening with light. Some of it we'll cover in this course, and some of it we won't, because light turns out to be pretty odd. But that's one of the weirdest things about it. And it really requires us to have an expanded understanding where we don't just think of light as being either a particle or a wave. We have to think of it as being both at the same time, and in a lot of ways being something different than either.